Welcome to the free response questions of the 2013 AP Physics C Electromagnetism exam. Let's jump right into it. Got my 45-minute timer starting now. All right, let's scroll down to our first question. The goal is just that I'm going to do them and hopefully get them right because I'm taking the exam next week. So we have a very long, solid, non-conducting cylinder of radius r, and it has a positive charge of uniform volume density rho. A section of the cylinder far from its ends is shown in the diagram above. Let r represent the radial distance from the axis of the cylinder. Express all answers in terms of r, big R, rho, and fundamental constants as appropriate. The first question is just asking us to derive an expression for the magnitude of the electric field at a radius that is less than big R, and to draw an appropriate Gaussian surface on the diagram. So first off, we don't really have a diagram here, but let's go ahead and draw out. Here is this cylinder that they're talking about. All right. And if we're going to be using some kind of Gaussian surface to derive this electric field, we need it to be along an equipotential. So if this is the axis of the cylinder here, what we really want to do is put some kind of cylinder around this axis. So let's put some cylinder of radius r right here, r less than big R, and let's apply Gauss's law to this cylinder. So by Gauss's law, I guess let's just write down this is question 1, part A. By Gauss's law, we know that the double integral over this cylinder of the electric field dotted with some unit area is going to be equal to the enclosed charge divided by epsilon 0. The electric field here is constant, so we can rewrite this as just the electric field at that value. And the total surface area, which is this term over S, is going to be the surface area of the cylinder, 4 pi r squared. Q enclosed is the enclosed charge. Because we have a uniform volume density rho, this is just going to end up being rho times the ratio of this cylinder as opposed to the large cylinder. So how much volume is in here? It's going to be the volume of the cylinder. The volume of the cylinder is going to be pi r squared times its length. Let's denote that with r. Remember, this length is going to have to cancel out in the end. I also forgot that this surface area needs to be multiplied by length, of course, all divided by epsilon 0. So what we get, dividing both sides by pi by r squared, is, oh, something strange happened here. Of course, the surface area is not 4 pi r squared, that's the sphere. So what we want instead is 2 pi r, which is the circumference of a circle times the length. So we divide the pi, the r, and what we end up with is that E equals rho, and then the L's go away, the pi's go away, there's 1 r left over 2 epsilon 0. This is our answer to A. And it looks like we're taking a lot of time blabbing, so let's move on quickly to part B, which asks the same, except now r is greater than big R. So again, Gauss's law holds. We're going to have a constant electric field times the surface area is going to be 4 pi RL again. The only difference here is that instead of saying that it's going to be the uniform volume density of charge rho times the volume of the cylinder we're dealing with, it's just going to be of the part of the cylinder that we've enclosed, because the cylinder does not extend out indefinitely. So instead of pi r squared L, we're going to have pi big R squared L over epsilon 0. And let's scroll down a bit for space. This tells us that the electric field for part B is going to be very similar to the one in part A, except now we're going to divide off our pi's. We're going to have rho, the L's go away, r squared over, and then we have 4. Where did that 4 go last time? Oh, right, it came into the, it was just a 2. I did this wrong again. This is 2. I don't know why I keep on messing up my surface area of a cylinder. So let's get this here, 2 r epsilon 0. now we're meant to, let's box it up. Now we're meant to graph the electric field as a function of radial distance from 0 to 2r, explicitly labeling all of the things. So let's get a nice gray for our graph. It's a bit crooked, but hey, we're tough on time, so no time to fix it. So first thing to notice is that the electric field is increasing linearly as we go out while r is less than big R. So let's just slap on a line there. What is the maximum going to be? It's going to be when r is big R. So rho big R over 2 epsilon 0. And after this point, when r is larger than big R, we see this big R squared term here, but that's a constant. So what we're going to end up with is a 1 over r term, which is going to make some kind of concave up decreasing slope here. And so, excuse me, we've labeled this maximum. We've got 0 here where it's starting, 0 here where it's ending. This is a horizontal asymptote, which you can denote with this. And this is at y equals 0. Cool. That should be everything for that question. Just to make it clear, let's also draw a dashed line here to show that this is all happening exactly at r. Of course, then I don't draw it exactly over r. This is all happening at r. So close enough. Now, we're going to derive an expression for the magnitude of the potential difference between r equals 0 and r equals big R. So this is part D now. I don't know how much of this is going to be occluded by the timer. I wonder, are we good? Yeah, okay, we're good. So if we go here now, we see that, let me scroll down more so you guys can definitely see this. We're in part DI. Recall that the potential difference, so this is the change in potential from 2 points A to B, is the negative of the integral from A to B of the electric field dot, whatever direction we're going. So if we're finding the potential difference from r equals 0 to r equals r, we're going to have A equals r and B equals 0. Excuse me. So, A equals 0, B equals r, right. And then it's negative because we're really going from r to 0, not 0 to r. So we have that the change in potential, well, that's a weird triangle. The change in potential is going to be the negative integral from 0 to big R of the electric field inside the cylinder, which is going to be rho r over 2 epsilon 0, this one. So rho r over 2 epsilon 0 dr. This is just the negative of, we pull out all the constants, well, really we don't need to. We'll just make this r squared over 4 epsilon 0 evaluated at 0 and big R. And if we finally evaluate this, we find that remember this is asking for the magnitude, so we can really say the magnitude of this potential is going to be, let's chop off the negative sign because we're taking absolute value, just going to be rho big R squared over 4 epsilon 0. That concludes part DI, and as for part DII, is the potential higher at r equals 0 or r equals big R? What you got to remember with potential is that it's asking how much energy did it take to move some positive test charge from infinity to the point you're talking about. To move a positive test charge from infinity to r equals r, let's say that takes some energy. Well, to move it again from r equals big R to r equals 0 takes more energy. So it's always going to be at a higher energy when you're inside some positively charged surface. And we know that the cylinder is positively charged because we know rho is positive. So the potential is definitely going to be higher at r equals 0, not at r equals r. This is our answer for DII. And let's go down. The non-conducting cylinder is replaced with a conducting cylinder of the same shape, blah, blah, and the same linear charge density. So now we're asked, oh my goodness, something happened. So now we are being asked to do this new graph. So let's pull up that nice graph color, try to make it straighter this time to some avail. And so we've got, again, r, got 2r, And now we're going to do it, except it's a non-conducting cylinder being replaced with a conducting cylinder. So remember, inside the cylinder, now the electric field is always going to be 0. What that corresponds to is that the charges are all moving out to the surface. So we've got 0 here for the start. And then at R, all the charge bunched up on the surface, it all starts to act. So we've got some kind of discontinuity there. And then when we pick up here, we are exactly where we used to be with rho big R over 2 epsilon 0. And we continue the same exact, that's not looking the same. We continue the same 1 over R descent that we saw in this graph up here. It's just that all the charge that used to be distributed uniformly within the volume, now it's all at 0 because it's a conductor and all the charge is at the edge. So again, let's make this easy to read by adding in that nice dashed green line. Except it's not dashed, so let's actually dash it. All right, that is a wrap for problem 1. We've got 4 minutes extra time if we're assuming we're taking 15 minutes question. So let's put it to good use on question 2. Great. Looks like we're at the bottom there. So let's scroll over a bit and do question 2 in this new column. Oh, how high up can we go? Pretty high. Okay. So just say this is our area. Question 2. In a lab, you set up a circuit that contains a capacitor C, resistor R, switch S, and a power supply, as shown in the diagram above. The capacitor is initially uncharged. The switch S, which is initially open, can be moved to positions A or B. Indicate the position to which the switch should be moved to charge the capacitor. So remember, if we want to charge the capacitor, what we need is some kind of complete circuit between the capacitor and the battery. So let's take position A. Position A, you've got some kind of complete circuit between the capacitor here and the resistor R. But the battery is not connected up, so nothing was actually going to flow, unless the capacitor is charged, but it's not. We're told it's uncharged. So we needed to go through B, because we look through B, then the battery goes here, down through B, up to the switch. Yes, it has to go through resistor R, but it's going to be charging up the capacitor. So for question 2 here, we say AI, we want it to go through switch B. All right, now let's attempt II. II says on the diagram, II. On the diagram above, draw a voltmeter that is properly connected to the circuit in a manner that will allow the voltage to be measured across the capacitor. Remember, when we have an ammeter, we want it in series so that it measures the current, because series is defined as the same current. When we have a voltmeter, we want it defined in parallel, because parallel is the definition of same voltage. Remember the example of 2 light bulbs connected in parallel to one battery. They'll both be equally bright. The battery will be drained twice as fast. So let me sketch up this circuit here so that we can draw in our circuit component. So this is point A of our switch. This is the switch S itself. This is the resistor with resistance R. And just finishing up point B and the battery with some EMF, E. Where do we want to draw the voltmeter? Well, we want it to measure the voltage across the capacitor. We need it to be in parallel. So let's pick 2 points here that are right next to either side of the capacitor and draw a nice voltmeter right along them in parallel. Boom. Question 2AII done. Now let's keep this in view. Let's move on to part B. After a long time, you move the switch to discharge the capacitor, and your lab partner starts a stopwatch. You collect the following measurements of the voltage across the capacitor at various times. So you've got some time and some voltage. Now we're discharging. So we wish to determine the time constant tau of the circuit from the slope of a linear graph. All right, I'm just going to throw this out there here. We want to remember that for an RC circuit, which is what we're dealing with, the time constant here is equal to, or I can never remember, it's equal to RC, not 1 over RC, because our equation is the V at some time, the voltage, is equal to the initial voltage times e to the negative t over the quantity RC, and we define the time constant to be whatever makes it e to t over the time constant. So the time constant here is RC. Yeah, okay. So this is something we're going to need to be remembering throughout the duration of the problem. Time constant is equal to RC. And so we wish to determine this time constant. So part BI is indicate two quantities that you would plot to obtain a linear graph. So remember, our equation here is that voltage is equal to the initial voltage times e to the negative t over RC. Somehow, we want to calculate RC. So we need to find some way to get it linear. We need it in the form y equals mx plus b. Bam. How can we do that? We need to take it out of the e. How do we take it out of the e? Natural logarithm. So let's take the natural log of both sides. You get that the natural log, let me switch a color, make the thing a little more vibrant. You get that the natural log of v is equal to the natural log of v naught e to the negative t over RC. The right-hand side, multiplication of two things in a logarithm, take them out. You get the natural log of v naught plus the natural log of e to the negative t over RC, which is just negative t over RC. And maybe you see where this is coming in. This is the natural log of voltage. This is just some constant. Who cares? We're calculating the slope. We find that the natural log of v is equal to negative 1 over RC times t. So if we plot natural log of v versus t, the slope is going to be negative 1 over RC. So we find that the slope is going to be negative 1 over time constant. We find the slope, we find the time constant. So part 2 says use the remaining rows in the table above to record any quantities that you indicated that are not given. We indicated natural log of v. They didn't give us natural log of v. So let's calculate natural log of v. Let me just make a quick table here so that we can write our values down. How many? We need 5 boxes, so I'll make 6 so we can indicate the original value. Oh, whatever, I made too many. All right, so we are calculating here the natural log of the voltage, which is in volts. And for 6 seconds, we need the natural log of 252, so I'm just going to be calculating this on my calculator at home. This is 5.52. This is going to be volts. Then we have the natural log of 74, which is equal to 4.30. Then we have the natural log of 33, which is equal to 3.49. Look here how these are decreasing approximately linearly. So something's working out. We're going to get a useful slope here. 2.30, and finally, the natural log of 6 is equal to 1.79. Great. All right, let's scroll down. On the axes below, graph the data from the table that will produce a linear relationship. Clearly scale and label all units, all axes including units, if appropriate. Draw a straight line that best fits your data. All right, so let's scroll down here to get a nice graphing place. So let's give ourselves plenty of room. All right, so here we are going to be graphing time on the bottom. This is going to be in seconds. Let me scroll over a bit so that hopefully you can see everything. Let me check that. Make sure you can see everything. It's pretty good. Maybe this helps. Yeah, okay, that's better. Now you have all the numbers. So we've got time there. We've got the natural log of v here, which is in volts. And we've got time going from, what was it, 6 seconds and then adding 12? Yeah, 6:18. So we've got 6, 18, 30, 42, 56, if I'm not mistaken. Oh, 42 plus 12 is not 56, it is 54. All right, let's do this. Let's graph this. A natural log is going to be ranging through 6-ish to, let me get the 3 in place. Let me get 2, 1, 4, and 5. For 6, we've got 5.52. It's like 5.5-ish. For 18, we've got 4.3. It's like there-ish. For 30, we've got 3.41. It's like there-ish. For 42, we've got 2.3. It's kind of there. For 54, we've got 1.79, which is there. So let's draw an approximate line of best fit. Something like that. Great. Downward slope as expected because we have a negative here. And let's scroll down. Now, part D says from your line in part C, obtain the time constant. Cool. Let's do that. So we know that, let me copy this table down. It's going to be useful. And let's scroll over now that we don't really need to have any of that info anymore. So now what we're looking to do is calculate a line. So remember, our equation was slope equals 1, -1 over the time constant. We got to calculate slope. So this happened at t equals 6. Final one happened at t equals 54. So let's calculate that slope, which is rise over run, is equal to the rise, which is going to be 5.52. The final minus the initial, so 1.79. So let me type this into my calculator. 1.79 minus 5.52. That is negative 3.73 divided by the run. So how many seconds did we go through? 54 minus 6, 48. Let's calculate this division. So negative 3.73 divided by 48. That is this thing, negative 0.0777. And now let's find -1 over this, because, right, we arrange this, we multiply tau, we divide slope, blah, blah, blah. So we divide 1 divided by this, multiply it by -1, and we get our final sparkling answer that the time constant is none other than 12.868 seconds. That's pretty cool. All right, final part of the problem. We've got about 7 minutes to do it. Looking pretty good on time. Oops, at the bottom. All right, let's read it. In the experiment, the capacitor C had a capacitance of 1.50 microfarads. Compute an experimental value for the resistance R. Hey, we have time constant equal to RC. We know the capacitance. Let's calculate the resistance. So what we get is that the resistance, just divide by C, the resistance is going to be the time constant divided by C. So the resistance is going to be 12.868 seconds divided by 1.50 microfarads. This is going to be something that my calculator will tell me. Can't stop rhyming today. When I type 1.50 microfarads, I'm going to type 1.50 times 10 to the power of -6 into my calculator. And what a large number. Let's ask for that maybe in scientific notation. It's going to be 8.578 times 10 to the 6th ohms. Hope that's correct. Guess it seems decent. Gut checking, maybe. I don't know. So let's box this guy up. Oh, and we stopped writing which problem this was. This is problem part D. This is problem part E, part I. Moving on to part II. On the axes in part C, used a dashed line to sketch a possible graph if the capacitance was greater than 1.5 microfarads, but the resistance was the same. Justify your answer. Remember, the slope is 1 divided by the time constant. So it's saying, hold the capacitance, increase R. So if we hold the capacitance and increase R, that's going to say that tau is going to get greater. So tau is going to be bigger. That means that this fraction as a whole, -1 over tau, because it's in the denominator, is going to get smaller, because the denominator is getting bigger. And a smaller negative number, smaller in magnitude at least, is a higher slope. So we're going to go from a more steep negative slope to a more shallow negative slope. And we're going to start at the same initial voltage, right? We're going to start at the same place here if we were to get this line all the way back from 0. The only difference is that we're going to be going down less quickly. So let's draw ourselves a nice dashed line here to represent a slightly shallower version of what was happening in part C. Yeah, that's decent. And it looks like it would start about the same place that this guy would start. Right there. Yep, great. All right. 19 minutes. Looking good. Let's do question 3. All right. Scroll over. Whoa, too high. All right. Question 3. The figure above shows a circular loop of area 0.25 square meters and a resistance 12 ohms that lies in the plane of the page. A magnetic field of magnitude B directed into the page exists in the area of the loop. The field varies with time t as shown in the graph below. So here is some kind of graph. Initially, it's an inverse exponential, or I should say exponential decay. And then we've got some just flat, linearly going down, and more flat. So let's just write out what we're at. This is question, let's keep consistent colors. Question 3. Oh, you probably can't see that if I write it in the very corner. Okay. Let's write it here then. That's better. Question 3, and we're on part A. Specifically, part A, I. Derive an expression for the magnitude of the induced EMF in the loop as a function of time for the interval t equals 0 to t equals 8. I almost said magnetic instead of magnitude. I was just primed for that. So remember, the induced EMF, by Lenz's law, is the negative change in the magnetic flux over time. This is negative. The flux is the area of the loop times the amount of field going through it, at least if it's perpendicular. So we can say A, B, C. Just kidding, it's just AB. A is constant in this case, so we get negative A times the change in the magnetic field. Of course, between times 0 and 8 seconds, the magnetic field is just this expression they give us, 1.8 e to the negative 0.05 t. So let's crunch out this derivative. The induced magnitude of the induced EMF is going to be negative. The area, we're told, is 0.25 square meters. And the derivative of this, pull out the constant, is going to be 1.8. Chain rule the top, negative 0.05. Put in the original expression, e to the negative 0.05 t. Looks good. Let me calculate out all these constants. So you have negative 0.25 times 1.8 times negative 0.05. That comes out to, let me just do one thing, boom. Okay, that comes out to the EMF equaling 0.0225 times e to the negative 0.05 t volts. Let's just put that unit in there. Volts. Okay. Box it up. Oh, that line went too high. Line's going too high again. Gotta get control of those lines. All right. Let's move on to part I. Aye, aye, Captain. Calculate the magnitude of the induced current in the loop at time t equals 4. This is simple exercise and plugging in t equals 4 to the expression we got above. So let's just write it out. If we were getting graded on the AP exam, a grader would like to see that you're showing your work, so that even if, say, you made a calculator error, you would still get possibly all the credit in the answer. Let's take that times, so e to the negative 0.05 times 4 is going to be 0.05 0, 1, 8, 4 volts. And we almost got tripped up because I almost just called it calculating the magnitude of the induced EMF. They're asking for current. Oh my god, it's important to read carefully. So if we recall Ohm's law, we have that V equals IR, favorite equation ever. So if we divide both sides by R, current is equal to the voltage, which we just helpfully calculated, divided by resistance, which we are told is 12 ohms. So the actual answer is going to be what we just found, this many volts, divided by 12 ohms. And so our final answer after reading the question is this over 12, otherwise known as 0.00153 amps. Let's box this guy up. Oh yeah. Let's move right along. Part B. Oh wow, only 3 parts on this question. Part B is going to be to sketch a graph of the induced current I in the loop as a function of time from t equals 0 to t equals 18 seconds on the axes below, assuming that a counterclockwise current is positive. Let's get ourselves some nice axes to work with. So here we're going to have 4 seconds, 8 seconds, 12, 16, and then I guess we just jumped straight to 18. Cool. And so here we're going to have time in seconds and the current in amps. And on the top we've got counterclockwise, on the bottom we've got clockwise. Nice, we've reproduced their graph now. So let's look at what we have. The first thing to notice is what direction, right? Is the current going to be clockwise or counterclockwise? That's going to tell us most of the information. So we look at this loop, right? We notice that the magnetic field is going into the page. This is where you might want to get that hand out of the pocket and get doing the right hand rule with me. So the current, keep on saying current. The magnetic field is into the page. The graph of the magnitude of the magnetic field shows it's always either constant or decreasing. So it's always going to be either counterclockwise or 0 or clockwise or 0. Let's figure out which one. Because it's decreasing, that means that the magnitude of the magnetic field downward is decreasing, which means that the current is going to be such that it opposes the change. The change is a decrease in the amount downward, which is to say an upward. So the current is going to point such that your thumb is downward as you curl your fingers. That's clockwise. So you really got to get your hands out for this, right? Decrease in going down is some change upward. So you want to oppose that. You go down, thumb points down, right? Like make a thumbs down. Look at your fingers. They curl clockwise. With your right hand, of course. So we know we're always going to be in this clockwise region. And then let's just look at this one more time, right? For the portions 8 to 12, 6 to 18, there's going to be no induced EMF because the magnetic field is not changing. Magnetic field produces EMF and current when it changes. The magnitude has nothing to do with it. It is always the change. That is Lenz's law. So it's from 8 to 12 and 16 to 18. So from 8 to 12, oh my goodness, let's get some green. From 8 to 12 and 16 to 18, we are solidly 0 with no change. And from 0 to 8, right, we calculated that the EMF is some kind of decaying exponential, and the current is just that same decaying exponential divided by something. So we're going to start here from 0 to 8 at some kind of point here with our current, and we're just going to experience some light exponential decay here. Let's make it a little more jarring, actually. Yeah. Some light exponential decay until we hit 8, and when we hit 8, of course, we're going to stop, go straight down to 0. As for the 12 to 16 period, we're decreasing linearly. And so our graph is going to have a constant, is going to be constant because the change is constant. But notice the change is also greater than everything that happened in the 0 to 8 period, so it's going to be higher than all of it, all of the 0 to 8 period, but it's going to be constant. So let me actually just do 2 points here and draw a straight line between them. This is what our graph is going to look like for part B. Yep, looks good. Part B, part II. Let's do that now. II. I love saying that. For the time interval 12 to 16 seconds, justify the direction of the current you've indicated in your graph. Right, so I just gave that verbal justification to you. So let's just write it out. Right, so we have the magnetic field is pointing into page. I would recommend using more grammar if you were doing this on the actual AP. The magnetic field is into the page and decreasing. Right? This is just the same as an upward change. By Lenz's law, we have that the current will be such that it opposes the change, right? Current opposes change. Opposes change. And so that means that by the right-hand rule, we have right-hand rule says a downward current. Sorry, downward means clockwise, right? You got your thumb out, right? I'm counting on you. You put your thumbs down with your right hand. You gave like thumbs down, like boo, and then you noticed you extended your fingers out, right, into a claw while you're giving that thumbs down. Your fingers curl clockwise, like a clock would tick around and around, right? So you can add a few words here to make it more comprehensible. But because I've already explained that in words, I feel the justification is fine. All right. That brings us to, wow, the final part. These exams are so short because they are split into 2 parts. Part C. Calculate the total energy dissipated in the loop during the first 8 seconds shown. Power is the current times the voltage. So, what is the current? It's a little annoying to calculate, so let's just put in the exact same. Remember, Ohm's law, V equals IR, implies I equals V over R. The equivalent, power equals V squared over R, because we have our expression for the, we have the expression, here we go, for the voltage at a time t between 0 and 8 seconds. Let's get that here. Bam. And so we know the resistance is just going to be 12 ohms. So we have that the power is going to be this squared, 0.0225 e to the negative 0.05 t squared over 12 ohms. And the work done from 0 to 8 seconds is going to be the integral of this power from t equals 0 to t equals 8. All right, let's crunch some numbers. So the work is going to be, let's pull out some constants now. So let me calculate what is the constant. It's going to be 0.0225 squared divided by 12. It's going to get gross. So the power is 0.0000000 0.4218 times the integral from 0 to 8 of, you take down this 2 into the exponential to get e to the negative 0.1 t dt. So this is going to be this same ugly constant, which I wish I never had to write in my life again, times the integral, which is just e to the negative 0.1 t. Anti-chain rules, basically a simple u substitution. We just divide by negative 0.1. You can just think if we took the derivative, it would come out to just the original function from not 0 to infinity, 0 to 8. Cool. So what we get is, I hope this is going to be the last time I have to ever write down this ugly constant, times, so we get negative, well, 1 divided by negative 0.1 is just negative 10, so we can write negative 10 times e to the negative 0.8 times, minus e to the 0. That's 1. Let's just plug this all into the calculator. We get the ugly constant times negative 10 times the quantity e to the negative 0.8 minus e to 0. That's just 1. Syntax error. I think I had an extra parenthesis. And we arrive at the final answer that the work done is this many joules. Seems plausible. Yep, okay. This is our work done. Another way we could have written this would be as 2.32 times 10 to the negative 4th joules. Cool. Let's box it up. And that's a wrap. I suppose we should check our answers like good, diligent AP test takers for the remaining 3 minutes that we have. So let's look at the answer that I have the hardest time believing, which was from the previous problem, if I recall. It was that the resistance is so dang high. I can't quite believe that. So let's just check our work. First, let's just scroll back up. Let's make sure we're good. We were doing on the axes in part C. No, sorry. This was part EI. In the experiment, the capacitor C had a capacitance of so many microfarads. Calculate an experimental value for the resistance R. Tau equals RC. We divide by C, we get R equals tau over C. I guess we're just dividing by a really small capacitance. Let's see how this shapes up if we fiddle around with the formula. So if the time constant was longer, that would mean that somehow the resistance is larger. That doesn't make much sense. I would expect it to be that if the resistance was larger, it would take less time for the circuit to run itself out, the capacitor's energy. Also, math doesn't lie. So, oh, right. I get confused with these things because for some reason, geniuses decided to define the time constant like this. Why the heck? Anyway, so it's kind of really the other way around, which makes so much more sense. Think of it as like 1 over RC is like a quasi, like, this is like technically 1 over RC. So I believe this now. It is basically because we're dealing with such a small capacitance that the resistance has to be so large that the capacitor takes a long time to discharge because it does not want to go through the resistor. Alright, that's decent. Let's just briefly check our answers, not like we really have time to change them at this point. Does this integral look right? Rho r over 2 epsilon 0. R squared over 2. Take the 2, multiply the 2. The 0 goes away. The r becomes big R squared. magnitude, magnitude, bam, multiply by -1 to make it an absolute value. All right, this graph looks solid except for that point that I really just don't want to change. The electric field here seems pretty good for part B. Yeah, this all looks solid. It also kind of needs to because we're out of time now. All right. I hope you enjoyed. Could do a follow-up video checking the answers. All right. Enjoy your APing, and remember, the AP is not the end-all be-all. Learning it is.